Hi everyone, so today I'm going to tell you about Metal, which is a metadata-hiding file sharing system. And this is joint work with Rota Popa. Okay. So there are many end-to-end encrypted file sharing systems, both in academia and in industry. In this system, we have users who store the file on the server under a key that only the user knows. And the problem with the end-to-end encryption is that there is still metadata leakage. Like, for example, user identities and file access patterns. User identity may refer to like who read or wrote the file. File access patterns may refer to which file is being read or written. And I now want to show you a specific example. Like in this picture, if the doctor wants to read one of the files, the attacker sees the following information. The attacker knows that the doctor is the person who accessed the file. The attacker also knows that the file is file number 1. And the attacker also knows the access control list of the file 1. I now want to show you a more concrete example. That is how file access patterns can be used to break the privacy. So let's consider a doctor who stores some treatment information on the cloud. And we assume that all these files are end-to-end encrypted, which means that even the file name will also be encrypted. Well, we want to show that this is still not sufficient because let's show an example. If now when we have a patient comes to visit the doctor will look up a specific treatment file on the server. 1 second, sorry. Like if the patient asks the doctor if the patient has diabetes, the patient will access a file about diabetes. And then if we have the patient who has cancer, another file will be accessed. So we can see that the attacker will see some of the files have been accessed. And this is a problem. This is problematic because if you know the file access frequency, and there is also a public database on like how frequent each disease will happen, then the attacker can actually use this number to infer what the disease, what each file is about. So now the attacker knows what the disease each file is about, and even though our file names are end-to-end encrypted. And this allows the attacker to do a very powerful attack, because now if we assume that Alice comes to the doctor, the doctor will now read a treatment file, like for example, the first file. Now the attacker knows that Alice may have cancer. Okay, so as we can see, metadata leakage is a big problem, and what can we do about it? A very relevant work is PIR-MCORAM, which is a single server system that provides security against malicious users. PIR-MCORAM can hide a lot of metadata, but it has a problem that is very expensive. In fact, in the paper, they provide a lower bound that is for any single server construction. If you want to hide the metadata, the computation will be linear to the number of files. And in particular, in that paper, they have to scan all the files in the storage system. And this actually is not very good because it will be very slow. In our experiment, we show that if you store 1 million files in the storage, it may take about 30 minutes to access one of the files. And another solution, Anonymous Run, uses a different approach. And they assume a different setting, which we have 2 semi-honest servers that do not collude with each other. And this will have the benefit that now you can bypass that lower bound. But the limitation of the anonymous run is that it does not support file sharing and also run very expensive zero-knowledge proofs. The zero-knowledge proofs are used to prevent against malicious users. And in this paper, we propose a new system called Metal, which also uses the same threat model, but we have the additional benefit that we can support file sharing, and we also have a better performance. So Metal as a file sharing system consists of 3 components. The first 2 components are for access control and permission sharing, which I will not cover in this talk. And in this talk, I will focus on the oblivious storage. So as for the threat model, Metal assumes 2 servers that are semi-honest and do not collude with each other. And in addition, we assume some users can be malicious. Our goal is to provide privacy and efficiency. And here, by privacy, formally speaking, I mean that for any given access should be oblivious amongst all the files accessible by the honest users. And we store the file using a layout like this. We store all the files encrypted on one of the servers. And the key to decrypt the file will be secretly shared between the 2 servers, such that the 2 servers can then run some protocol and decrypt the files. And what protocol can we use to do this? One of the protocols is secure 2-party computation, which I now will have a very brief introduction. So in secure 2-party computation, we have 2 parties. Here are our 2 servers. They have some input, and they want to compute a join function over these inputs and obtain their outputs. The security guarantee of secure 2-party computation is that each server only learns its own input and output. And our system uses something called reactive YAWS protocol, which provides a very special secure computation in which you can maintain the state inside the computation. This reflects that our secure computation is more likely a continuous service rather than a one-time computation. So now I can talk about our first strawman, about how to store the file on the server and access the file obliviously. So when we have a user who wants to read a file, the server can run the secure computation, find the files that the user wants, and return the file back to the user. Because of the security guarantee of the secure 2-party computation, no server sees the file. And this one is working. It provides the security guarantee, but it has a very big problem. It's actually very slow. And the reason for that is that when you want to store files inside secure 2-party computation, it will become quite expensive. Like if we use YAWS protocol, each bit of the file needs to be represented in terms of some crypto value, which will be pretty large. So to do that, our solution is to use a cryptographic primitive called oblivious RAM, which is an efficient way to access a file without revealing which file. And here we have an ORAM client and an ORAM server. When the client wants to read a file, the client engages a protocol with the ORAM server. And the security guarantee here is that the ORAM server doesn't know which file is being accessed. And the efficiency guarantee is that the ORAM server only accesses very few number of files. So now we can use that to develop our second strawman, in which we are going to use ORAM. We arrange our file on the ORAM server, Now the question is, where should we put the ORAM client? And the idea is that, should we place that on the user? No, because if user have the ORAM client, the user will be able to access all the file on the server. So we use a very different approach by putting the ORAM client inside the two servers' secure computation. So now, if the user wants to access a specific file, the request is forwarded into the secure two-party computation, which can check whether the user have the permission to read this file. Then, if like the secure two-party computation feel that the user should be allowed it to read the file, the secure two-party computation can run the ORAM protocol with the ORAM server, obtain the file, and sends the plaintext back to the user. However, this one is actually still not efficient. We still have the privacy guarantee, but the problem is that it's not efficient. So we have a number that if you just use this simple construction, you will still have a very, very big latency. So we want to improve the efficiency, and the problem is how do you do that? So we first have an observation that the reason it is slow is because we put data inside the secure two-party computation protocols. And we find that many secure two-party computation protocols are not suitable for storing data. So we introduced a new technique called synchronized inside-outside ORAM, which we split the original ORAM into one called index ORAM and one called data ORAM. The index ORAM will only store small indices of the file, like some identifier of the file. And the data ORAM will be the one that stores the actual file data. And we want to ensure that our secure two-party computation protocol, here the YAWS protocol, only access the index ORAM. But when we split the two ORAM, there is a problem. Now we need to synchronize these two ORAM. So later I will show you that we try to maintain that these two ORAM are synchronized, such that when we find a file using the index ORAM, we can find its data in the same location. Okay, so now I also want to talk a little bit about how we do the data encryption in the data ORAM. So in data ORAM, we use L-gamma encryption to encrypt the data. And it has some benefit. One of that is that if you know the public key of the L-gamma encryption, you can re-randomize the ciphertext. And this will make it easy for us to develop oblivious protocols. Okay, so now I want to explain a little bit more about how oblivious runs works and how we modify it in our inside-outside design. In ORAM, the access to a file usually is downloads some data on a specific path. And the client sends a path to the server and obtain the data on a specific tree path. And in our construction, we surely want the secure two-party computation to only access the small indices. So now, only the indices is there. And the ORAM client, which is inside the secure two-party computation, will be able to find out which one of the three indices that is sent back from the server is the one of the desired file. So here, we can see that the second file is the desired one. And the ORAM client actually cannot reveal this value directly to the two servers. But one thing the ORAM client can do, and we will use that, is to secret share this position, which is that the second file is the desired file, to the two servers. And we will use this information later to get that file data from the data ORAM. So now we take a look at the data ORAM. We know that the second file on the path is the file that we want. We just need to find a way to get that file. And this brings us to a challenge, that is how to obtain this data obliviously. And we remind you that we previously sequential this position 2 between the two servers. And what we find out is that you can design a simple public key protocol to do this. And what we do is that we use a protocol called sequential doubly oblivious transfer, which allow the two servers with the sequential of the position to obtain a re-randomized ciphertext of the second data block, which is the desired file data. And the re-randomization ensures that both servers cannot infer the position from the resulting ciphertext. And this will allow us to obtain the ciphertext of the file. Then we can run threshold decryption to decrypt the file so that our user can obtain the plaintext of the file. Okay, another operation that ORAM needs to perform is update. And in an update, the user basically chooses to pass, send them to the server, and the server will returns the data block on these paths. And the client will now update the ciphertext on this path and also return the update version to the server. And of course, in our inside-outside ORAM design, we want the secure two-party computation to only operate and update the indices. But that is a problem. If you update the indices, what if I need to update the file data? So we need to apply the same update operation to the data ORAM. And how do we do that? So firstly, we have an observation that the operation of the ORAM update actually we can express that as a permutation, because most of the operations are nevertheless just moving the data. So if we can express them as a permutation, here, let's call that sigma. We can then sequential this permutation, and then we can use this sequential to run our next protocol, which will operate on data ORAM. So now we have our data ORAM again, and now we are going to update it. And the solution is that, and the challenge is that we want to apply this permutation to the data ORAM, but there is one requirement: we should not reveal this permutation. Well, remind you that we have the sequential of the two permutation, and what we do is that we can have the two servers, each server performs a sequential of the permutation in turn. So let me show you what will happen. So we start from the first server, who obtain the ciphertext from the data ORAM, apply a permutation, which is like the first share of the permutation, sends the data to the second server, which will apply the second permutation, and then we'll write the permuted result back to the data ORAM. And this actually can allow us to apply the permutation while we don't reveal the permutation. And during permutation, we also ensure that all the ciphertexts are re-randomized so that none of the server can infer the other party's permutation shares from the ciphertext. Okay, so therefore we have our synchronized index ORAM and data ORAM, which provide us with a very good performance improvement. Actually, this one is quicker by directly applying secure two-party computation and ORAM by about 20 times. And now I want to talk a little bit about our implementation and evaluation. So we implemented methods and also evaluate its performance. We place the server and the client in different locations because we want to simulate the situation that they are in different trust domains. And from this figure, you can see that the file access latency is growing linearly to the size of the file, and it grows logarithmically to the number of files in the whole system. And as you can see, the file access latency is actually quite promising because it's only a few seconds. And this is a very big improvement from the prior work, although they provide like different security guarantee and are under different threat model. Okay, and Metal will be open source in this website. And thanks for your listening, and feel free to ask questions.
Hi, excellent talk, thank you. One question, regarding the Al-Gamal encryption. So you're encrypting basically the content of the file. So my question is, of course, Al-Gamal is not what is called CCA secure, meaning, it's a malleable kind of encryption. I mean, is this a problem for your system, or is it something that you will address in a different version?
This actually has something to do with our threat model, which that we assume the server to be semi-honest. So in our design, I didn't find a problem that will require the CCA security. But I think that's a very good point. That is, if we want to achieve malicious security against the server, I guess we do need something like that, or zero knowledge proof.
Okay, thank you.
I just want to clarify. So you encrypt the entire file with Al-Gamal, so therefore it will be slow if the files are bigger and bigger. Am I correct?
Yeah.
And after this clarification, so when you add new files, you have to change the circuits that you are using, right? The circuits are for fixed files, the number of files, or fixed set of files?
So it's like we initialize the system with a specific number of the file. And if you working under this limit, then you don't need to pay additional cost when you add more file.
I see. So you have to have an upper bound on the number of files you have.
Yeah.
So you fix the circuit based on that upper bound. If
Yeah.
I reach that upper bound, then I have to reinitialize everything.
Yeah, but
restart every process.
We can improve over that, although we didn't mention that in the paper, is that there are some excellent work on making the ORAM resizable, such that you can later just let the ORAM go larger. While the cost is that you kind of need to tell the server at one moment you need to increase the number of files, because that's actually a leakage if the server knows the number of the file in the system.
But you need to reconstruct the entire SPC circuit, right?
Yeah, during each, I think is that in the reality computation for each file access, you need to create a new gobble circuit in the protocol.
And that gobble circuit size does depend on the file system size, correct?
Yeah, but does not depend on the size of each file.
Sure.
Yep.
Sang Wei Kang again.